Could a small team really move an 80-ton stone across England without wheels? That question drove experimental archaeologists to test ancient building theories, and their results often overturned long-held assumptions. By the end of this video, you will discover how 15 modern experiments verified or shattered our understanding of medieval and pre-modern engineering. You will find out how the Inca made walls that danced during earthquakes and how Roman concrete still heals its own cracks centuries later. Each case reveals not just ancient ingenuity, but also the limits of our own assumptions. Which ancient mystery do you think will be solved next? One of the most puzzling mysteries involves the smaller stones at Stonehenge. These blue stones, each weighing a were transported from the Preseli Hills in Wales, over 150 miles away. How did Neolithic builders move them across such rugged terrain long before the wheel was widely used in Britain? In 2019, a team from University College London decided to put an old theory to the test. They built a wooden sledge and laid a track of logs, creating a rolling roadway. Then they hitched the sledge to a small group of volunteers and asked them to pull a 1-ton stone over a short distance. The results surprised even the researchers, with the logs acting like rollers and a little water poured on the track to reduce friction. Just a handful of people could move the stone with steady effort. The experiment validated the ancient technique of lubrication, something historians had long suspected but never proven through physical trial. But the test also revealed a sobering reality. Moving a stone a few dozen yards was one thing. Covering 150 miles required thousands of people working in relays, clearing paths, maintaining the log tracks, and hauling the sledge day after day. The experiment showed that while the method was feasible, the manpower and organization needed were staggering. It paints a picture of a society far more coordinated and determined than we often give them credit for. Yet moving the bluestones was only half the challenge. Once they arrived at Salisbury Plain, the builders still had to lift them into position, a feat that required equally clever engineering. A 7-degree external ramp would have needed more material than the pyramid itself. That startling discovery emerged from computer simulations testing one of the oldest questions in archaeology. How did the ancient Egyptians lift the massive granite blocks that form the Great Pyramid's inner chambers? For decades, the leading theory involved a straight, sloping ramp built against the pyramid's face. As the structure rose, workers would drag stones up an ever-lengthening incline. But that simple solution came with enormous drawbacks. A ramp steep enough to minimize distance would require a slope too severe for pulling such heavy loads. A gentler ramp, say 7 degrees, would stretch for over a mile and demand a volume of rubble and earth that construction estimates showed could exceed the stone used in the pyramid itself. The logistics became absurd. In response, French architect Jean-Pierre Houdon proposed a radical alternative. He suggested that the builders constructed a spiral ramp inside the pyramid, hidden within the outer layers. This internal passageway would wrap around the core as the pyramid rose, allowing workers to drag stones up a gradual incline without wasting material on a massive external structure. Houdon put his theory to the test using scaled physical models and detailed computer simulations. The results showed that an internal ramp could feasibly accommodate the geometry of the pyramid while keeping the slope gentle enough for human power. The external ramp theory, meanwhile, was mathematically untenable. Houdon's idea gained traction, but it raised new questions about friction and maneuverability. Pulling a 40-ton granite block around a tight curve inside a narrow tunnel presents its own challenges. Physical experiments to measure the friction of stone on mudbrick or wet sand are still ongoing, and researchers continue to refine the model with each test. These hands-on trials keep the debate alive, much like the inquiries that now turn to another marvel of ancient engineering, the secret recipe of Roman concrete. The recipe for Roman concrete remained lost for over 1,000 years, yet some of their harbor structures still stand after 2 millennia of relentless wave action. Geologists at the University of Utah and MIT became curious about this remarkable durability and decided to take a fresh look at samples from the ancient port of Baiae. They analyzed the mineral composition and found something unexpected. Instead of simply crumbling with age, the concrete had actually grown stronger. The key ingredient was a rare crystal called aluminous tobermorite. This mineral forms slowly over time when volcanic ash, lime, and seawater react together in a specific way. The researchers recreated the mixture in the lab using these exact components and confirmed that the chemical reaction continues for centuries. As seawater seeps into tiny cracks, it triggers the formation of more crystals, which seal the gaps and reinforce the structure. This self-healing property was not an accident. The ancient builders deliberately chose volcanic ash from the region of Pozzuoli and combined it with quicklime in a hot mixing process. They understood that the resulting material would harden even in aquatic environments, something modern Portland cement cannot do without extensive additives. The experiment proved that Roman engineers had perfected a form of chemistry that we are only now beginning to fully appreciate. Their concrete was a living material designed to heal itself over generations. Yet not every ancient building tradition relied on chemical reactions. In the high Andes, another civilization achieved a different kind of permanence through sheer precision. The Inca built walls so carefully fitted that a knife blade cannot slide between the stones, and they did so without mortar, wheels, or even iron tools. Such precision raised a question that earthquake engineers wanted to answer. How could walls built without mortar survive the violent shaking that regularly topples modern structures in Peru? The Inca constructed their finest stonework in a region where the ground trembles often, yet many of their fortress walls and temple foundations remain standing centuries later. Researchers at the Pontifical Catholic University of Peru decided to test that durability directly. They built replica walls using the traditional Inca method, fitting irregular stones together so tightly that a blade could not pass between them. Then they placed these replicas on a shake table, a machine that simulates earthquake motions. For comparison, they also built conventional mortared walls of similar size and shape. The results were dramatic. The mortared walls cracked at the joints and collapsed within seconds under moderate shaking. But the Inca-style walls did something unexpected. Instead of breaking apart, the stones shifted slightly, rocking and settling against each other as if dancing with the tremor. When the shaking stopped, many stones had moved a few millimeters, but the wall remained intact. The engineers discovered that the secret lay in 2 features. First, the stones were cut with a slight trapezoidal shape, wider at the base and narrower at the top. This shape locked each stone into place under gravity, so upward shaking could not dislodge it. Second, each stone had multiple interlocking faces, not just flat sides. These irregular surfaces created friction and allowed the wall to absorb energy through micro-movements rather than brittle failure. The experiment confirmed that the Inca builders had developed a seismic resistant design through centuries of observation and trial and error. They watched which walls collapsed in past earthquakes and which ones survived, then refined their stone-cutting skills accordingly. This living knowledge was passed down without written plans, yet it produced engineering that rivals modern earthquake codes. The same spirit of patient testing and bold transport would soon apply to another iconic mystery, the moving of giant stone statues across a remote Pacific island. The towering stone heads of Easter Island have puzzled explorers for centuries. How did the Rapa Nui people move these colossal statues, known as moai, across a rugged island without wheels or draft animals. Some weighed as much as 80 tons and stood over 30 feet tall. For decades, the leading theory claimed that workers rolled the statues on logs, cutting down the island's palm trees to create rollers. But that explanation came with a troubling implication. If the Rapa Nui had stripped the island of its forests to move the moai, then deforestation was a direct cause of their civilization decline. Yet new evidence suggested something else entirely. In 2012, anthropologist Carl Lipo and his team from Binghamton University set out to test a very different idea. They suspected that the statues were not rolled but walked upright, rocked from side to side using ropes. To prove it, they built a 5-ton concrete replica of a moai and attached 3 ropes to its head. A small group of volunteers pulled the ropes, one on each side and one behind, and began to rock the statue. With each coordinated tug, the moai tilted forward and shifted its weight, taking a step. The team found that just 18 people could move the statue at a steady pace of about 100 feet per hour. Computer modeling confirmed that the rocking motion created a natural walking gait, using the statue's own center of gravity to prevent tipping. The experiment disproved the log rolling theory conclusively. Moving a moai on logs would have required hundreds of workers and an enormous supply of timber, which the island's sparse forest could not have supported. Instead, the Rapa Nui had developed a clever walking technique that allowed a small community to transport these monuments across miles of terrain. The test also explained why many moai were found along ancient roads, toppled and broken in ways consistent with sideways falls rather than rolling accidents. These stone giants had literally walked into place, but moving massive objects horizontally was only half the challenge. Once builders got a heavy stone to its destination, they still had to lift it into the air. How did medieval masons, working with ropes, pulleys, and wooden scaffolding, raise the immense stone vaults that crown their cathedrals? That question would drive another set of experiments, testing not how to walk a statue but how to hold a roof. The flying buttress solved a problem that had stumped builders for centuries. When medieval masons of the Gothic era decided to raise stone vaults higher than ever before and fill the walls with stained glass, they faced a dangerous force called lateral thrust. A heavy stone ceiling does not just push straight down, it also pushes outward, trying to spread the walls apart. The earlier Romanesque style had handled this by building walls so thick they were almost solid stone, but that meant small windows and dark interiors. Gothic architects wanted light, so they needed a way to catch that sideways push without relying on massive wall thickness. Their answer was the flying buttress, an external arch that reached out from the wall and transferred the thrust down into a sturdy pier on the ground. It was a brilliant solution, but for centuries we only understood it through drawings and surviving structures. Then, in the early 2020s, engineers at the University of Cambridge decided to put the design to a rigorous physical test. They constructed a 1:20 scale model of the flying buttresses from Notre Dame Cathedral in Paris. These replicas were built from the same limestone and mortar used in the original, carefully reproducing every joint and stone cut. The team then placed the model in a loading frame and applied forces that simulated the weight of the roof and the pressure of strong winds. They gradually increased the load and measured exactly how the structure responded. The results confirmed that the buttresses were remarkably efficient at redirecting lateral thrust, preventing the walls from bowing outward. More surprisingly, the tests revealed something about the joints between the stones. The builders had cut them not as rigid blocks but with slight gaps and angled surfaces. Under load, these joints allowed each stone to shift a tiny amount, absorbing energy like a series of small shock absorbers. This meant the entire structure could flex without cracking, a property that protected the cathedral during windstorms and settling. The experiment proved that the Gothic masons did not just stack stones. They engineered a system that used controlled movement to maintain stability. That same principle of intentional flexibility reappears in a completely different material, the wooden joints that hold together medieval timber frames. The same spirit of empirical engineering guided the hands of medieval carpenters who built the great timber halls and barns that still stand today. These structures often use a joint called the mortise and tenon. A tenon, a tongue-shaped end of one beam, fits snugly into a mortise, a rectangular cavity cut into another beam. A wooden peg called a trenail is then driven through both pieces to lock them together. For centuries, historians assumed that peg was the main source of strength, but modern experiments at the University of Bath changed that understanding. Researchers built full-scale replicas of these joints using green oak, the same wood medieval builders used. They loaded the joints in tension, pulling them apart, and in compression, pushing them together, while measuring the strain in every part of the assembly. The results were striking. The peg itself carried almost no load. Instead, the tight fit between the tenon and the mortise transferred the force across the joint. The peg only held the pieces in place during construction, preventing them from sliding apart while the building was raised. Once the structure was complete and the roof added, the weight of the building caused the tenon to wedge even tighter into the mortise. The joint became stronger over time. The tests also showed that many medieval joints were deliberately over-engineered. They used thicker beams and deeper sockets than strictly necessary. This suggests the carpenters worked from centuries of practical knowledge, building in safety margins because they understood how wood expands and contracts with moisture. They did not need calculus or stress analysis. They had observation, patience, and a tradition of passed-down skill. That same kind of deep, intuitive understanding would soon be tested in a completely different environment, where water, not wood, was the central challenge. High in the Andes, the Inca had built a city whose drainage system still functioned perfectly after 500 years. How did they manage water so precisely on a steep mountain ridge? Machu Picchu sits on a steep ridge between two peaks where rain falls heavily for half the year and the soil wants to slide. The Inca builders did not fight that slope. Instead, they designed a drainage system that worked with the mountain, channeling water away before it could undermine the foundations. Yet for decades, archaeologists assumed the system was simple, just a few open gutters carved into the stone. Then hydrologist Kenneth Wright took a closer look. In the early 2010s, Wright built a scaled model of one critical drainage channel within the sacred sector of the city. He pumped water through it at varying rates to simulate normal rain and then torrential downpours. He also added sediment to the flow to mimic the mud and debris that would wash off the terraces. What he discovered changed the understanding of Inca water engineering. The channel was not a straight groove. It was a series of shallow steps, each one dropping a few inches. That step design did something clever. As water cascaded down each step, it lost energy, slowing the flow and preventing erosion. But more importantly, the steps acted as sediment traps. Heavy particles settled on the flat treads while clear water spilled over the risers. At the bottom of each step, the builders had placed a row of small stone slabs, like baffles, that caught the finer silt. The result was a self-cleaning channel that remained open even during the heaviest storms. Wright tested the model with sediment loads that would clog a modern concrete drain within minutes. The step channel kept flowing. The system still functions today, nearly 5 centuries after it was built. When Wright and his team inspected the actual drainage channels at Machu Picchu, they found them clear of debris, still directing water safely off the site. The Inca had solved a problem that modern engineers often overlook: how to manage stormwater on a steep slope without constant maintenance. Their solution was not about moving water away as fast as possible. It was about controlling its speed and letting gravity do the cleaning. That same kind of ancient hydraulic insight appears in a very different landscape, where water was even scarcer and more precious. Deep in the desert of southern Jordan, the Nabateans carved a city from rock and built a water system that captured every drop from rare storms. While the Inca managed abundant rain on a slope, the Nabateans faced the opposite problem: almost no rain at all. The city of Petra, carved into rose-red cliffs in southern Jordan, receives less than 6 inches of rainfall each year. Yet this desert city supported a population of around 30,000 people at its peak. The secret lay in a water system so clever that it captured every drop from the rare but violent flash floods that swept through the canyons. Archaeologists from the University of Arkansas decided to test how this system actually worked. They reconstructed a small-scale section of a rock-cut channel and cistern based on surviving remains. The channels were narrow, only a few inches wide, and cut directly into the sandstone with a series of shallow steps. When the team simulated a flash flood by releasing a surge of water mixed with sediment into the channel, the results were immediate. The step design slowed the water velocity dramatically. As the flow cascaded down each step, it lost energy, and the heavier particles of silt and sand settled onto the treads. By the time the water reached the cistern at the bottom, it was clear. The system not only captured the water but also cleaned it, preventing the cistern from filling with mud that would be useless for drinking. The experiment showed that the Nabateans had engineered a self-scouring channel that required no maintenance between storms. They had transformed a desert into a thriving urban center, not by fighting the environment but by working with the force of flash floods. But not every ancient challenge required water management. Some required breaking through stone walls. That is where the next set of experiments turned, testing the medieval siege weapons that pounded castles for days. The trebuchet was a machine built for brute force. When its arms swung forward, a massive stone projectile could fly over 300 yards and strike a wall with devastating energy. Yet for centuries, historians debated whether that single impact could actually breach a properly built stone curtain wall. Some argued that a well-aimed shot might shatter the masonry in one blow. Others believed that medieval walls were simply too thick and resilient for any one stone to do the job. In 2005, a team of engineers and historians at Warwick Castle in England set out to settle the argument with a full-scale experiment. They constructed a working trebuchet based on surviving drawings and records from the early 13th century. The machine stood about 60 feet tall with a counterweight of nearly 10 tons. Then they built a mock section of castle wall, using the same materials and construction techniques that masons would have used in the year 1200. The wall was 12 feet thick at its base, built from local sandstone and packed with a core of rubble and lime mortar. The team loaded the trebuchet with a stone ball weighing roughly 250 pounds and fired it at the wall. The impact was stunning. The stone struck with a thunderous crack, sending fragments of mortar and stone flying, but the wall held. The team fired again and again. After each shot, they climbed down to inspect the damage. The first few impacts only chipped the outer face, barely penetrating the surface. It took over a dozen shots before a visible crack appeared in the masonry. Even then, the wall still stood. Only after more than 20 direct hits did the structure begin to show signs of serious failure. The experiment confirmed what many siege engineers had known from experience. A trebuchet could not smash a wall with a single shot. Siege warfare was a grinding war of attrition. Attackers had to maintain a steady bombardment over days or even weeks, pelting the same section of wall repeatedly until the mortar gave way and the stones began to tumble. This changed our understanding of how long a well-supplied castle could hold out. It meant that even a determined attacker needed time, patience, and a massive supply of ammunition. The test also revealed something else. The wall itself was not the only target. trebuchets often aimed at the battlements, the crenellations on top, to clear defenders from the parapet. A single stone could shatter those lighter stones easily. The real goal was to weaken the wall from above, making it unsafe for defenders to stand there while sappers worked below. The experiment gave historians a much clearer picture of medieval siege timelines, and it showed that a castle was not a passive structure. It was an active obstacle that forced attackers to commit enormous resources to overcome. But stone and mortar were not the only defensive materials that ancient builders mastered. In the jungles of Mesoamerica, the Maya created a surface that could repair itself over time. The Maya faced a different enemy than stone walls or siege engines. Time and moisture were their constant adversaries, and they found an answer hidden in the forest itself. In the humid Yucatan, where rain and humidity can erode stone within decades, the plaster floors and facades of Mayan cities have endured for over 1,000 years. Researchers at the University of Pennsylvania decided to find out why. They collected samples from ancient plasters at sites like Tikal and Capon, then analyzed them with powerful microscopes and chemical tests. What they discovered was a recipe far more sophisticated than simple lime. The plaster contained organic additives, including extracts from tree bark. These natural compounds altered the plaster's chemistry in a crucial way. During the curing process, the bark extracts created a higher pH environment, which encouraged the formation of calcium compounds that remained active even after the plaster hardened. When tiny cracks appeared from settling or thermal stress, moisture seeped in and triggered a chemical reaction. The calcium compounds dissolved slightly, then recrystallized as calcite, precisely filling the microcracks. The team recreated the plaster in the lab using the same ingredients and subjected it to controlled cracking tests. They found that the plaster did not weaken with small cracks. Instead, it actually strengthened because the calcite deposits fused the broken edges together. It was a self-healing material, exactly like the Roman concrete, but achieved with completely different ingredients. The Maya had essentially engineered a smart plaster that used the environment to maintain itself. This discovery shifts how we view Mayan construction, not as crude mortar, but as a carefully formulated composite designed to last through centuries of tropical weather. Now from the jungle to the marble quarries of ancient Greece, where builders faced a different challenge: how to lift columns weighing tens of tons into perfect vertical alignment. Getting a 20-ton stone drum to sit perfectly level on the column below it required more than just raw strength. It demanded a lifting system that could raise the block high enough and then lower it with surgical precision. The ancient Greeks built some of the most elegant stone structures in history, yet no detailed plans survived to explain how they hoisted those massive pieces. The architect Vitruvius wrote about wooden cranes several centuries later, but his descriptions left many questions unanswered. In the early 2010s, the Hellenic Institute of Ancient Technology decided to test those descriptions with a full-scale physical experiment. They built a replica column drum weighing 10 tons, using the same marble and the same cutting techniques as the original builders. Then they constructed a lifting device called a sheerlegs derrick. This simple but effective machine consisted of 3 long timber beams lashed together at the top to form a tripod. Ropes ran from the apex down to a winch system operated by a small crew of men. The team positioned the derrick over the replica drum, attached the ropes, and began to crank. The drum lifted smoothly, rising several feet off the ground. Then the crew swung it over the platform and slowly lowered it into place. The experiment demonstrated that a relatively small team, perhaps a dozen men, could handle a 10-ton stone using only timber and rope. But the test revealed something more important than just the lifting capacity. When the drum settled onto the platform, the crew had to adjust its position repeatedly. Each lowering left the drum slightly tilted or off-center. The team had to lift it again, shift the ropes, and try again. The process took multiple attempts to get the drum perfectly level and aligned with the one below. This showed that the real challenge was not lifting the stone but controlling its final placement. The sheerlegs derrick gave the builders fine control because the ropes could be adjusted from the ground, allowing small corrections as the drum descended. The experiment validated Vitruvius' design and also highlighted the skill of the ancient stoneworkers. They did not just haul blocks into the air. They developed a system that let them nudge tons of marble into exact alignment, one careful adjustment at a time. That kind of patience and precision would soon prove essential for a completely different kind of construction, one that faced not the challenge of dead weight but of living motion. On the stormy seas of the North Atlantic, Viking shipbuilders had mastered a flexible hull that bent with the waves rather than fighting them. Modern sea trials proved just how deliberate that design was. In 2007, a full-size replica of a Viking longship named the Sea Stallion from Glendalough set sail from Roskilde in Denmark bound for Dublin, Ireland. The voyage covered over 1,000 nautical miles across some of the most unpredictable waters in the North Atlantic. On board, researchers had installed strain gauges along the hull, sensors that measured how the wooden planks bent and twisted under the force of each wave. What they recorded changed our understanding of Viking shipbuilding. Instead of fighting the ocean's energy, the clinker-built hull worked with it. The overlapping planks, lashed together with flexible iron rivets and tarred wool, allowed the entire structure to twist and flex as waves passed beneath. A rigid modern hull of the same length would have transmitted that force directly into the frames, causing stress fractures over time. But the Viking ship absorbed the impact by bending, then springing back into shape. The computer models built from the sensor data confirmed that this flexibility was not a weakness but a calculated feature. It gave the ship two advantages. It reduced strain on the timbers, making the vessel more durable on long voyages, and it allowed the hull to ride over waves rather than plow through them, which improved speed and stability. The test left no doubt that the clinker construction was a mature technology, refined over centuries by shipwrights who understood how wood and water interacted at a deeply intuitive level. They had engineered a vessel that could survive storms that would shatter a stiffer boat. That same principle of controlled flexibility, letting a structure move instead of break, appears in a very different setting: the stone arches that carried roads and travelers across medieval rivers. The stone arch carried weight by turning downward pressure into sideways thrust. That lateral force had to be absorbed by the abutments at each end, otherwise the arch would spread and collapse. Medieval builders did not have calculus or stress diagrams, yet they routinely constructed bridges that spanned wide rivers and carried heavy traffic for centuries. The Pont du Gard in southern France, built by Roman engineers but maintained and studied by medieval masons, still stands as a towering example of arched masonry. The bridge at Avignon, with its famous broken span, shows the same structural logic in action. At the University of Bologna, researchers decided to test that logic with physical models. They built scaled arches from individual voussoir stones, the wedge-shaped blocks that form the curve. Then they applied point loads to simulate the weight of a laden cart crossing the bridge. Measurement instruments tracked how the forces traveled through each stone. What they found was elegant. The load did not push straight down through the arch. Instead, it traveled along the curve, compressing each voussoir against its neighbor until the force reached the abutment. As long as every stone remained in place, the arch could hold many times its own weight. But the experiment revealed a critical vulnerability. When the researchers removed a single voussoir from the middle of the span, the entire arch collapsed instantly. That single missing stone broke the continuous ring of compression, and the remaining stones fell inward. This matched historical records of how medieval bridges actually failed. Siege engineers knew that knocking out the keystone, the crown stone at the top, could bring down an entire section. The test confirmed that medieval bridge builders understood thrust lines, the invisible path of force through a structure, even though they had no equations to describe it. They learned through observation and tradition, building arches with carefully cut stones that relied on gravity and friction to stay locked together. The same principle appears in a far older device, one built not for crossing a river but for sensing the ground shaking beneath a palace. In ancient China, an engineer named Zhang Heng created a seismoscope that could detect earthquakes from hundreds of miles away. How did it work, and could it really sense building vibrations before people felt them? In 2005, scientists in Beijing put that question to the test. They built a full-size replica of Zhang Heng's seismoscope based on historical descriptions and bronze casting techniques from the 2nd century. The original device stood about 6 feet tall and looked like an ornate wine jar with 8 dragons circling its body, each holding a copper ball in its mouth. Below the dragons, 8 bronze toads waited with open jaws. The inner mechanism centered on a pendulum suspended from the lid. When the ground shook, the pendulum would swing, triggering a lever that released one of the balls. The ball would fall into the toad's mouth with a loud clang, indicating the direction of the tremor. But for centuries, historians argued whether such a simple pendulum could actually work, or if the device was mostly symbolic. The modern team placed their replica on a shake table and programmed it to simulate various earthquake motions, from gentle rolling to sharp jolts. They started with a weak tremor barely perceptible to a person standing still. The pendulum swayed, but not enough to release a ball. Then they increased the intensity to a moderate earthquake strong enough to rattle furniture. This time, the pendulum swung decisively, striking the lever, and a bronze ball dropped into the toad's mouth with a clear ring. The scientists repeated the test dozens of times, varying the direction and strength of the simulated quake. In every case where the tremor exceeded a certain threshold, the device correctly released the ball in the direction opposite the vibration source. The experiment proved that Zhang Heng's invention could reliably detect distant earthquakes and indicate their bearing. It could not measure magnitude or pinpoint distance, but it gave palace officials an early warning, often before the shaking arrived, because the device responded to the faster traveling P waves, while the destructive S waves and surface waves followed moments or minutes later. That precious time allowed people to evacuate unstable buildings and brace for the main shock. The test confirmed that this wasn't just a clever ornament. It was a functioning early warning instrument 2 millennia ahead of its time. The same principle of using a suspended mass to sense ground motion is still used in modern seismometers today. Zhang Heng's bronze dragons were a first step toward understanding the invisible forces that shape the earth, a quiet reminder that ancient engineers, like the builders of stone arches and clinker ships, learned to read the world around them with tools forged from observation and experiment. And as we look back across these 15 cases, a common thread emerges. Each test, each rebuilt wall or recreated crane, brought us closer not just to knowing how something was done, but to respecting the ingenuity of those who did it. The experiments gave numbers and mechanisms to stories that had been passed down for generations. They turned legend into science, and in doing so, they revealed that the past was never as primitive as we assumed. The builders, the sailors, the stone cutters, the plaster mixers, they were all engineers in their own right, working with nature to create structures that would outlast their own lives. And perhaps that is the deepest lesson of all, that the technology we call modern is really just a conversation with a much older wisdom, one that still speaks to us through the stones and timbers left behind. Across these 15 experiments, a pattern emerges that is both humbling and inspiring. Ancient builders were not simply copying traditions by rote. They were solving problems systematically, testing materials, observing failures, and refining their techniques over generations. Each reconstructed wall, each replicated joint, Each sea trial confirmed what many historians had long suspected but could not prove, that the engineers of the past were pragmatic scientists in their own right, working not with equations but with hands and eyes and years of accumulated wisdom. The tests did more than verify old theories. They overturned others, forcing us to abandon comfortable assumptions about primitive methods. The Inca walls that danced through earthquakes, the self-healing Roman concrete, the walking statues of Easter Island, all of these discoveries remind us that ingenuity is not a modern invention. It is a human constant shaped by environment and necessity. And what of the questions that remain? The experiments we covered in this video are only a beginning. New techniques in imaging, material science, and digital simulation promise to uncover even more secrets hidden in ancient structures. The next generation of experimental archaeologists may finally show us exactly how the Great Pyramid was built, or how the Antikythera mechanism was calibrated, or how the Nazca lines were surveyed with such precision. Each answer will likely raise two new questions. That is the nature of discovery. So I have one question for you out of these 15 cases. Which experiment surprised you the most? Was it the earthquake-proof Inca walls, the walking moai, or perhaps the self-healing Maya plaster? Let me know in the comments below. If you enjoyed this journey through experimental history, please like and subscribe. Every click helps us bring more stories like these to life, stories that connect us to the quiet brilliance of those who came before. Thank you for watching, and I will see you in the next video.